Sorry for that. Yeah. Second collaborator is Kazumasa Okabayashi, who is a postdoc in YITP, and Takahiro Terada, assistant professor in Nagoya University. And this talk is basically improvement of previous application of resurgence to quantum cosmology by people working on cosmology. And I will start with the introduction, and then I will explain a model of quantum cosmology which I use today. And finally, I will give a reflexive decomposition and resurgence of the model. Okay, let me start with the introduction. So today, object of which we are interested. I'm interested in physically is path integral of gravity. And it's not well defined, but schematically, this is a if we adopt the path integral definition, schematically we imagine something like that, and where SL is the action of gravity, and this is in Lorentzian signature. And people also sometimes consider Euclidean version of this path integral, but it's often said that the Euclidean version has a technical problem because it is known that the action of Euclidean gravity is unbound, and then unbound, and this is real. And when it is unbound, this kind of integral is obviously divergent. Even if this integral, even if we have a good definition of path integral measure. So apparently it looks ill-defined. But the people have also found Euclidean gravity looks useful because they found some interesting use of Euclidean gravity. Yeah, for example, there are sometimes a discussion of a black hole entropy in the context of Euclidean gravity. Also, there is a proposal by Hartle and Hawking on conjecture on early universe. Well, anyway, there's some interesting proposal. And there are some tunneling arguments. But although it looks interesting, but it seems to have a technical problem. But for Lorentzian case, it may or may not be refined, but this is the path integral is purely oscillatory integral. So there is a possibility that the above one is conditionally convergent. And now, central question of this talk is that is there any good connection between Lorentzian gravity and Euclidean gravity? And here, I'd like the message of this talk is that Picard-Lifshitz theory is seems useful to answer this question, at least partially. And next, I will give us some detail on this theory. Yes. Hmm? No, 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 no. Okay, even if we ignore that problem, for example, if we take Einstein gravity, then, for example, if we consider, okay, path integral can control, okay, to the path integral, okay, there is, for example, if we have a space-time giving a negative curvature with arbitrary negative curvature, arbitrary large negative curvature, and then this gives the SE to be infinity. Yeah. Yeah. We could also say that. Yeah. Mm-hmm. Yeah. Mm-hmm. It's also possible. So, okay, so, okay, so, yeah, there are a lot of problems of this, in this describing this. Okay, so I would say it's apparently unbounded if we use naive, yeah, yeah. So in this sense, if we get some good UV description, this problem may not be a problem. Yeah, but yeah, I'm not sure, but it's still interesting to, it's still interesting to ask this question. Yeah. Well, we basically fix topology. So I will, okay, so instead of considering path integral of a generic spacetime, we will use a approximation called mini superspace approximation. I will tell you a detail. Yeah, so I will discuss that even if we consider very simplified approximation, there is a interesting phenomena related to Picard-Lifshitz things and resurgence. And I'm not sure here I should whether I should review Picard-Lifshitz theory. So what's the Picard-Lifshitz theory briefly? So suppose we have some one-dimensional integral along some integral contour with under some condition. Then we can schematically decompose the integrals over in terms of Lifshitz symbol. And Lifshitz symbol is steepest descent associated with saddle point xs. And this is a steepest descent. Or Lifshitz symbol. Associated with saddle point xs. and the coefficient is known to be integer, and this can be 0 or non-zero. And if this is 0, this means that the saddle point XS do not contribute. And while it is contributing when this is not 0. And in general, note that the saddle point is not generally on original entire contour. So it's generically complex. I mean, in the physics, usually see to be a real axis. Then it's useful to use Picard-Lifshitz theory to judge whether the complex saddle is contributing or not. Here, I'd like to apply this technique to the path integral of Lorentzian gravity. Then, in general, some complex configuration corresponds to Euclidean spacetime. Then, by using this technique, we may get good interpretation on connection to Euclidean gravity. So this is what we want to do. I want to discuss today. But this is not our original idea. There is a previous study which try to apply Picard-Lifshitz theory to Lorentzian path integral for gravity. It was done. It was back in 2070 by Trock and collaborator. So let me briefly explain what they did. It was done by Feldbrücke, Reynolds, Trock, and Trock in 17. And there are similar papers following this paper. So in this work, they tried to apply Picard-Lifshitz theory to a toy model for the gravitational path integral. For gravity with a positive cosmological constant. Yeah, capital lambda is positive cosmological constant. And by toy model, I mean, this is a model based on approximation called mini-super space approximation, which I will explain in detail later. Anyway, by applying this approximation, the technical problem is reduced to ordinary one-dimensional integral. And for ordinary one-dimensional integral, it's easy to apply Picard-Lifshitz theory. But from my viewpoint, the application of Picard stress theory to this problem was not complete. So I'd like to improve their analysis. And why it was not complete? Because their analysis was done only at the Stokes line. And from the viewpoint of Picard shift analysis, so if we encounter Stokes line at the parameter region of interest, then it is a kind of beginning of interesting problem, but somehow they stopped it. And at Stokes line, of course, decomposition in terms of Lipschitz symbol becomes ambiguous. Then this makes physical interpretation unclear, especially for which saddle point contribute to the path integral of gravity. So here, as in usual analysis of resurgence or application of Picard stress theory, we deform a parameter to go away from Stokes line and then try to come back by limits. And physically, we consider deformation of H bar, and physically H bar should be real and positive, but here we deform H bar to be complex. Then we apply Picard-Lipschitz or theory or symbol decomposition here, and then try to come back to the original real positive H bar. Then, so as in usual application of Lipschitz symbol in some parameter region, the Stokes multiplier have a discontinuity for some saddle point. Then, as in usual scenario of resurgence, this kind of ambiguity is cancelled by Borel resummation, ambiguity in Borel resummation of another saddle point. So in this sense, there is a cancellation between the ambiguity of Lipschitz symbol decomposition and ambiguity of Borel resummation of quantum gravity correction. So this is an overview of our main result. And next, I will give a detail of derivation and result of our main result. And so do you have questions for overview part of my talk? Good. Um, okay. After okay. Okay. For this case, okay. After we get the one-dimensional integral, Euclidean case looks also very defined. Very defined. Yeah. 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 I will explicitly show the form of integral later. And finally, okay. Next, I will set up. I will explain a concrete model of quantum gravity, quantum cosmology, which used in this talk. And starting point is usual action of general relativity with boundary in time direction. Here K is a extrinsic curvature, and we take lambda to be positive, and take a unit such that 8 pi g equal 1. G is a Newton constant. Then we use approximation called mini superspace approximation. And this is likely oversimplifying approximation. And in this approximation, we restrict ourselves to consider space-time, which is homogeneous and isotropic. So yeah. Then so this is a kind of actual starting point. Then we substitute this form of space-time to the original action, and then instead of considering a path integral over a generic metric, we consider path integral only over n and q. And after substitution, this is technically become something similar to quantum mechanics. Here K is a curvature constant of a three-dimensional part. Then Then engage n dot equals 0. So we define a model by the following path integral. So technically, this is a starting point. So because of this condition, we have an ordinary integral over n, and then we have a path integral for q. Yeah. Although this involves path integral, but the action is quadratic in Q, and then we can perform the path integral over Q exactly with some regularization scheme. Finally, we get the ordinary one-dimensional integral, and I switch the integral variable from n to x. And here S on shell x is given by a polynomial of x. Okay, it's sextic polynomial of, no, it's not the normal polynomials. There is a weird part, but S is given by this, so the highest order is 6. And parameter alpha, beta, and gamma are given by physical parameters as follows. Yeah, and physically, alpha should be positive, and gamma should be 0 or negative. And so here we will apply Picard-Chess theory to this integral. Yes.
I'm not sure of the relationship between that law, which is very explicit, and what you were talking about in your introduction, where you also mentioned superspace and your problem theory. Are the two the same, or were they different applications?
That's the same. Yeah, they try to apply Picard-Chess theory to this integral. Yeah. Yes. Sorry, choice of what? Sorry. Gauge. Gauge. Well, are you asking why is this condition good or not? Well, okay, this condition is technically convenient. Okay, anyway, we fix the variable to in some gauge. Yeah, for this, but good point for this is that we have a finally we can transform make this problem to ordinary integral. Yeah, but I'm not sure if this is best. But yeah. Okay. Okay. This was essentially done in this step, and I skipped. Yeah. I skipped many things here. Yeah. Okay. Okay. This computation was not done by us, and so it was done in this paper or some other paper. Yeah.
So basically,
Yeah.
instead of integrating over the whole three-dimensional space of all the metrics and dimensions,
Yeah.
you choose the secret ones, you integrate over n and q.
Mhm.
There is some gauge freedom on n,
Yeah.
fixed gauge freedom using whatever topology doesn't give you anything new, and
Yeah.
you reduce it down to this one-dimensional.
Yeah. Good. Yeah. Thanks.
And again, going back to Paolo's question from before, the topology speaks, you don't take any sort of orbital or quotient, the topology, you just get one.
Yeah. 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 And so anyway, yeah, this is kind of our starting point. Okay, let us rewrite the problem in a convenient notation for that analysis. And fx is I over h bar times the f on shell. And here we have 8 saddle points, which is given by integer 0, 1, 2, 3, and plus and minus. Yes, and depends on plus and minus. And parameters, some saddle points have a positive real value and negative value. And because of historical reason, we call saddle points giving negative real part, negative real f as a tunneling, and positive part, for positive part we call no boundary saddles. And now let us apply symbol decomposition to the integral. And there are two important properties for Lipschitz symbol. First important property is imaginary part of f is constant along the symbol. Also, real part is monotonically decreasing in this convention along the symbol. And then schematically, we have we want to decompose this integral in terms of the symbol, which is schematically given by this formula. Yeah, yes.
In terms of the magnitudes, I assume that given a saddle, you can probably find a solution to the equation of motion for n and q that gives you
Mm.
that particular action. So why are they called tunneling and no boundaries? What type of geometry are these?
Yeah. Well, okay, tunneling is clear. So, well, okay, so physically this is okay, this is supposed to be um, transition amplitude, yeah, between the geometry with size qi and qf, yeah, and there was an old paper by Blinking saying that, this should be exponential separate. There is a kind of tunneling phenomena, and then should behave like exponentially suppressed. Yeah, and on the other hand, in the proposal by Hartle and Hawking, they found a kind of exponentially large. They proposed, according to their proposal, the quantity should increase exponentially. Yes. Yeah. The saddle. Yeah. I will explicitly draw. Yeah. Yeah. And so we will see uh, there are differences on property of this decomposition depending on parameter region. And technically, this is basically classified by whether the inside of a square root becomes negative or positive. The simplest case is negative beta and this combination positive, 12 alpha gun plus beta square is positive. And if this combination is negative, we get more complicated structure. And most complicated case is a complement of the two cases. And in terms of physical quantity, this combination is given by this formula, but we don't have a clear physical interpretation for why there are differences between these three regions. But anyway, we will see the structure. Yeah. Yeah, first let me draw the Lipschitz symbol structure for the simplest case. We have a complex plane of x, and then we have 8 saddles. And especially we have 4 real saddles. And then symbol structures for some relevant saddle points are given by. And here solid line is a symbol or steepest descent. And dotted line is a dual symbol or steepest ascent. And in particular, the coefficient of the decomposition can be read from intersection number between dual symbol and the original intercontrol. And here, it's easy to get the symbol decomposition. So we get let's see. Yeah, by it's we can take this, this.
Here,
Hmm?
looks like there are Stokes line, but not really, right? The origin is a singular term of the action.
Yeah.
Involved connecting two saddles.
Ah,
The origin.
yeah. Good point. There is a tiny convergent region here. Yeah, yes. Yeah. Sorry. Yeah. For this case, structure is simple, and so we can say that there are 4 real. Okay, the 4 real saddle points are contributing saddle point. So we don't have any problem in this parameter region for interpretation. Yeah, except the subtle origin.
Sorry, what type of saddles are these?
Okay. This one gives the purely oscillating one. Yeah. Yeah, when S. Yeah, okay. This gives the S to be real. Yeah. Okay. Next, let's consider region 2. Here we have 8 complex saddles. And for this kind of structure, we have a problem on in interpreting which symbol is associated with which saddle. This is because, for example, for this case, actually there here this saddle, sorry, this symbol is passing multiple saddles, and so technically this is called Stokes phenomena. Then we have ambiguity in interpreting. We have ambiguity in Lipschitz symbol decomposition. And decomposition becomes ambiguous. Then we deform. Okay, this was when H bar was positive real. Then we deform H bar to be a complex value and try to come back to real positive theta. So next I will show sketch of simple structure for complex H bar. Okay. So, location of saddle is independent of theta. Okay, so let me first draw the symbol here. Okay, now all the symbols is passing only one saddle, so we don't have ambiguity, and so this is saying that we should choose we should pick up the two saddles. This is for positive theta case, and for negative theta case, the structure is like this. Okay, this is the structure, and so all the quantitative behavior is different, but it's qualitatively the same. So this is also saying we should pick up the same saddle points. So for this case, although theta equals directly at theta equals 0, we have a ambiguity on interpretation, but this is saying that theta equals 0 limit can have the same interpretation. And it's a, I think many people here are familiar with Resurgence, yeah, this kind of analysis. Actually, this is similar to integral of integral, similar to the integral of zero-dimensional pi-force theory. Here for real G, yeah, we also have a similar. Although this is not so complicated problem, but this integral also has a similar issue in the for the interpretation. So for complex, okay. Anyway, for in region 2, for complex H bar, we don't have ambiguity in interpretation. The same, there is a, we have a we have the same structure for the symbols. But I forgot to mention that. So in the previous paper by cosmology people, they basically stopped here. Yeah. Then at this stage, just by looking at this plot, so we are not sure about physical interpretation. And this structure, we have also seen that this structure is smooth between theta equal positive theta and negative theta. And physically, these plus type saddle points are interpreted as tunneling saddle points. So this result is saying that this results imply that for this region, only tunneling saddles contribute to the integral. So this is the result for region 2. And okay, I will finish in 5 minutes. And finally, we will see that region 3 has a more complicated structure. So in region 3, we will see that there is a discontinuity. There is a difference on qualitative structure of Lipschitz symbol. Yeah, first for positive, real positive H bar, symbol structure is like this. Oh, sorry. Yeah, again, we are in Stokes line. So let's take positive H bar. Sorry, complex H bar. Okay, here we have 4 contributing saddles. So here plus and 2 plus type and 2 minus type contribute. And what happens if we take negative theta? So now basically there are difference on minus type saddle points. So for positive theta, the L symbol of this guy was intersecting the original intent counter. But for negative theta, this no longer, this does not intersect the original intent counter. So here we only plus type saddle points contribute. So this means that there is a jump on Lipschitz symbol structure, especially the Stokes coefficient for the saddle minus types saddle point in here and here. And if we don't know about the standard scenario of resurgence, apparently this seems to say that the integral value of the integral is discontinuous at theta equals 0, but this is not true. Then, so if we know resurgence, we have some expectation on the structure. From standard resurgence scenario. So first, so we found there is a kind of discontinuity between between positive theta and the negative theta for the coefficient. Then expectation that if we consider Borel resummation of the h bar small h bar expansion of plus saddle points, then that Borel resummation also has ambiguity at theta equals 0. And that ambiguity is a minus of the ambiguity coming from the Stokes jump. So this is the expectation. And then we confirm we checked this statement to some extent. And So I will finish soon. So we have not checked for completely generic parameter, but we explicitly confirmed this for this when one of the parameter is 0 up to 100 order h bar to the 100. And for gamma equals 0, it's easy to get explicit form of a Borel transformation. Mm. 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 Yes, 12 alpha gamma plus beta square. Yeah. Yeah. So this region corresponds to here, and here I took gamma to be 0. Yep. So for that case, yeah, action is a polynomial, and we don't have a negative power of the integral variable. Yeah. Yeah. It's yeah, it's easy. Yeah, easy to perform at least for one of the third point. Yeah, and we also have a closed form for the whole integral. Yeah.
Typically, this is the case where you initial and you find out the same, right? So you're coming in between the same universe.
Yeah. At least for the size. Yes. Yeah. And it's explicitly given by a simple hypergeometric function. And this has a branch cut in real axis.
Maybe one of these F21 functions that have transformations with elliptic intervals.
That's how deep you study parameters.
No, just application. Because in the closed-loop analysis, I put
Mhm.
writers of all the triangle relations that 12 of them,
Mm.
some of them involve 6. So there may be very interesting algebraic transformation that makes it
Oh. Yeah, I was not aware of that. Yeah. So, okay, this is for x plus. And for x plus part, we perform the all of the part. We get all of the form for transformation. And for x minus, so we perform the perturbation by using mathematical up to h bar to the 100. Then, we explicitly confirm the expectation from standard scenario of resurgence. So although from the viewpoint of resurgence, this is technically simple, but it's kind of fast proper application of resurgence thing to the context of quantum cosmology. And so, I hope there will be more papers on applications in this context. Okay, let me stop here. Thank you very much. yeah. So good lesson is that okay. Uh, in of quantum cosmology, it's always important to ask what is a contributing saddle point in early universe or something like that. And this result is saying that in some parameter region, it's easy to ask, but in some parameter region, some other parameter region, there is an ambiguity for answering the question. So for example, in one, there is no difficulty on answering that question. For region two, we got a unique answer, but it was hard to answer that question just by looking at the physical H bar, positive H bar region. And in the last case, this is saying that there is no unique answer. So there are two correct interpretations, yeah, depending on whether we approach from negative theta or positive theta. So the lesson is that the first important question is not sometimes a well-defined question. Yeah, yeah.
Everything depends the difference
Mm.
between initial Q and final.
Yeah.
Yeah, so can we say that if the initial Q is this, then this universe is stable and
Mm.
moves suddenly to another
Mm-hmm.
universe?
Mm-hmm.
We cannot say that.
Yeah. It's also good way of answering. Yeah. So yeah. Uh,
So we could say
yeah.
your universe is stable
Mm-hmm.
at the quantum level, or
Mm-hmm.
we could say, oh, that
Mm-hmm.
universe is not stable.
Mm-hmm.
Probably depends on the initial Q.
Yeah. We can also yeah. More concretely, yeah. We can also discuss this aspect. Yeah. Yeah. Also, yeah, there are also similar different models on quantum cosmology, and so we could discuss if we want. Okay, if we want some certain point. Okay, if we want universe to be stable or something like that, then which model gives this answer or something like that. So there are, so I think there are potentially many applications. Yeah.
My question was almost the inverse of Dalton's. Let's forget all of the physics
Oh,
at the
oh, oh,
beginning.
oh.
Just look at the integral that you're dealing with.
Yes.
It seems quite possible that such a combination of polynomial plus inverse phi
Yes.
occurs elsewhere in mathematical physics.
Mm.
Have you looked for such applications?
Personally, I haven't seen. Yeah.
See, and that's why I'm
Uh,
particularly interested in this. This is the purely polynomial case with
yeah.
no inverse phi.
Yeah.
I really want to go and see whether this is in the classical form.
Yeah. For this case, yeah. For this case, there should be application. Yeah. Yes. Yeah. Yeah.
These special way for this curvature for which the model could be solved finally again. Because at the end of the day, you're solving some Schrodinger equation of the Fourier potential.
Mm-hmm.
It may happen that for some other parameter, potential
Mm.
intervals.
I see. Yeah, that's possible. Yeah, but we haven't studied. Yeah. Yeah. Relatively, it would be interesting to consider kind of exact WKB approach to the, the Euler duet. Yeah. Mm. Yeah. Yeah. So yeah. Yeah, here, yeah, we studied only from the integral viewpoint. Yeah, yeah. Yeah. Yeah, we haven't studied it. Yeah, 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 yeah. It should be interesting to study. Yeah, yeah.
One of the cases of Lorentzian ODE model. I mean, the potential is very simple. Is it possible to go beyond this mini superspace approach?
Uh, where previous study seems, yeah, also consider the case with matter with particular angular momentum. Yeah. So yeah, it may be, well, okay, space-time is still inside of space, but there may be a way to include kind of from mini space. Yeah, but yeah, yeah.
Maybe a version where you get a finite dimensional field, but it's not of a single variable, but of multiple variables.
Oh, multiple variable. Uh, maybe if we want to, I'm not sure, but so uh, yeah, I guess so. If we take a bit different answers, mimicking, for example, topology change, yeah, there may be a way, I'm not sure. Uh, yeah, if we include matter in very particular way, there may be a way to rewrite the Parsing integral in terms of, yeah. I'm not sure. Yeah, but it should be, yeah, it should be interesting to look for, yeah, more tractable model, yeah, tractable situations, yeah. Yeah.
Okay, since I don't see questions, let us thank Masazumi again.
Thank you.